Okay, guys, so for the next one, what we're going to do is we're going to talk about step 3, which is your critical values and test statistic. Okay, now, your critical values and your test statistic, they are one of basically 3 ways that we make a decision with a hypothesis test. Okay, so the whole idea, we've already talked about setting up a null and alternative hypothesis. And basically, what it comes down to in the end is we want to choose, are we accepting your null hypothesis, or are we going to reject your null hypothesis, which therefore means we are assuming our alternative was true. Um, so there are 3 ways. Your critical value and test statistic is one way, your p-value is a second way, and your confidence interval is a third way. So all 3 of these last steps have to correspond with each other, have to basically all make the same decision for us. They should all support the same decision. And that's really important because if you're working a problem and your last 3 steps do not support the same decision, you've made a mistake somewhere, because they should all support the same thing. So your critical values and test statistic, we have to kind of think about this in 2 different ways. We have our one-tail test and our two-tail test. So for our one-tail, this is where H sub A is either less than or greater than some number. And then our two-tail test, this is where our alternative hypothesis utilizes not equal. So with the one tail, we have 2 different things. We have a less than and we have a greater than. So I'm going to have 2 different pictures here. All of these are based on this picture of a normal distribution. So pretend that one's normal. I know it looks a little skewed. So let's say here that we have H sub A, mu is less than, H sub A, mu is greater than. So the reason that we call this a one tail is because less than and greater than, hold on. Okay, sorry about that. Less than implies that we are looking to the left side of our curve. Greater than implies that we are looking to the right side of our curve. Now, these lines that I drew, these are your critical values. So I'm just going to put Z critical. It could be T critical, depending on what type of test. Then over here with our two tail, here's what it's going to look like. We're actually going to have 2 critical values because we simply think it's not equal. We don't know if it's less or greater. We're unsure. It could be one or the other. We don't know. We just know it's not equal. So basically, here's what happens with your critical values. Your critical values get set, and these are kind of this line in the sand. And basically, your critical value is how many standard deviations away from the mean can we be and still be an acceptable value? How far can we go and it's still normal? It's not too far from the actual mean that it raises any red flags. So it's this cutoff line between what is normal and acceptable versus what is abnormal, unacceptable. So again, normal, acceptable, abnormal, unacceptable. Same thing. In the middle, this is the picture we're more familiar with. This is our normal, acceptable range of values. Anything that falls outside of these lines, we would consider unusual. So all of these little shaded regions, these are what we refer to as the reject region. And on a two-tail test, we have 2 of those. Okay, so those are your critical values. The critical values are, these are the cutoff values for what is acceptable. Okay, then what we have is we have something called a test statistic. Now, your test statistic, let me look at this and make sure I tell you it exactly right. Okay, so your test statistic shows how many standard deviations away from the mean our sample is. So basically your test statistic, sorry, I didn't realize we had that picture on there. This is kind of like a z-score for your sample. Okay, so we have this idea based on, based on the null hypothesis, what we think that this mean might be approximately. And what we're trying to figure out is when we take a sample, is it relatively close to that? If it's relatively close to that, then we're going to go ahead and say, okay, maybe your original claim wasn't so bad after all. But if our z-score is too big, if our sample is too far away from that original hypothesis, that kind of raises some flags, and we start to think, okay, maybe your original claim is not right after all, because it's really unusual that my sample would be so far away from your mean if that was really the mean. And I'll explain that a few more times as we go, because I think that that's confusing, but it's also super, super important. So I'll reiterate that a few times as we go. So what we look for is this test statistic, which again is basically your z-score for your sample. And we try to look at where that test statistic falls on this scale, basically, or on this curve. So if your test statistic falls out here, then we reject the null hypothesis. Because again, let me reiterate this. Let's say we get this test statistic that's way out here. Your test statistic is a z-score. So let's say my z-score was like 3. That's what we know is unusual. We reject the null hypothesis because they're saying if the null hypothesis is really the true mean, then even when we take a sample, shouldn't it be pretty close to that true mean? If you remember the activity that we did with the pennies, the average age was 23. And when you took samples of the pennies, didn't a lot of your samples come back with a mean pretty close to 23? So it makes sense that all of those samples we took would have a pretty small z-score. They were pretty close to the mean. However, what if we got a sample, that had a mean of 2? That raises some red flags. That tells us there's either something wrong with our sample, or that original claim that the actual mean is 23 maybe isn't correct. So if your test statistic falls out here in this shaded area, that is when we reject the null hypothesis. It raises some flags, and we think the original claim, the original hypothesis, might not be right. Now, if it's in this non-shaded area, okay, we either reject the claim or we fail to reject. So I like to think in statistics of this as we never admit defeat. Okay, our goal is we want to prove people wrong. So it's always really satisfying when you get to reject the null hypothesis and say, haha, I was right. But we don't always get to do that. But I like to think of it like this. We never admit defeat. So even if I can't reject the null hypothesis, I never flat out say, okay, you were right, I accept it. I just say, I don't have enough evidence to reject your null hypothesis. So for now, I fail to reject. So those are our two options when we are running a test of hypothesis. We either reject the null hypothesis or we fail to reject the null hypothesis. So that kind of gives us a little bit of context, a little bit of information about critical values. The only other thing that I need to show you here is some formulas. Okay, so here's some formulas for you. When we are doing these tests, we're either going to have to find a z-critical in a test statistic or a t-critical and test statistic. So to find your z-critical, first of all, you have several options. Is it a one-tail test or a two-tail test? And then if it's one tail, which tail is it? So over here, if it's on the left side, so if it's a less than, that is a left tail test. So one tail, left side, so left tail test. If it's on the right side, that's your greater than. Here's our z-critical. It's a one tail, right tail test. So based on what we know just about kind of the number lines, this one is going to be on the left, so it's negative. The one on the right is going to be positive. So in order to find your z-critical on the left, what you have to do is normal CDF. This is left, so it starts at negative E99. Oh shoot, not that. Wrong one, sorry. Inverse norm, your alpha value, 0 and 1. And again, you just have to know if it's on the left, it has to be negative. If it's on the right, it has to be positive. Then to find your test statistic is denoted by just Z, where this is Z critical. Z is x bar minus mu divided by sigma over the square root of n. Now, what if we have a two-tail test? That means we have one of each. So here we're going to do inverse norm, alpha divided by 2, 0 and 1. That's for your z-critical. And the reason that we divide alpha by 2 is because that area has to be split equally among our two tails. And we'll talk a little bit more later about what alpha means, but alpha is kind of your probability of something being abnormal. So that's kind of your probability that we're looking for. So most cases it's going to be 5%. So we're looking for what is the cutoff for this bottom 5%, or what is the cutoff for the top 5%, or that 5% gets split among two tails, so it's 2.5%. Now for your t-critical, same pictures, except we're using inverse t. So if it's a one tail, it's just alpha and then your degrees of freedom. If it's a two tail, we have to again imagine that alpha being cut in half. And then your test statistic is x bar minus mu divided by s over the square root of n. And hopefully these two formulas look familiar. These are basically your z-score formulas when we talked about the central limit theorem. So again, I feel like I'm throwing a lot of information at you, but once we start doing some examples and pulling it all together, it will make more sense. So we will keep going on. We've got 2 more steps to go.